All right, so if there's no other, are there no other questions from homework? I'm an optimistic fool, so I'm going to take that to be good. Okay. So, one thing I didn't discuss in section 3.1 is this idea of a 4-fact family. Just sounds like, friend, you don't want to go to their house. You're like, your family knows 4 facts. It doesn't sound good. I don't know. Hopefully one of those facts is how to make dinner if I'm going to eat out there. All bad jokes. I love it. So 4-fact family. So let me give an example, an easy example. What is 4 plus 7?
11.
11. And then, so therefore, what is 7 plus 4? Without doing any thought? 11. Therefore, what is 11 minus 7? 4. And therefore, what is 11 minus 4? 7. 4 facts. If you know any one of them, you know all the other ones. So let me give you one that's not so simple. What if A minus B equals C? Give me another fact. Give me what would go here.
B minus A equals C.
No.
Oh.
B minus
So
C
you can
equals A.
say, sorry.
B minus C equals A.
B minus C.
A minus C equals B.
All right, look. Look here. The total minus one piece is the other guy. And then don't be switch.
Okay.
So
Right.
B plus
So if A minus B is C, what's the biggest thing up here then?
A.
A is the biggest dude. So what is A minus the other chunk?
C equals B.
The first chunk, right? I love it. Now give me some addition stuff. If A minus B is C,
B plus
what equals A?
B plus C.
B plus C, or you could write it as
C plus B.
C plus B. There's your 4 facts. I just had to give you any one of them and you can give me the other 3. All right, so let's do one more example that'll kind of tie into something else. What is 4 base 9 plus 7 base 9? How far away from 1, 0 is this? What would be 1, 0? Yeah, it's 2 away. Is everybody cool with that? Because this will become 1, 0 when it hits the base, which is 9.
Yeah.
So, isn't this got 2 in it?
Yeah.
Couldn't you write this as right? Except make it more like a 9 instead of a freaking Q. We don't want base Q. Do you? No. So then, what did you say this was? 10. So then this will be 12 base 9. And a way to kind of check this, 4 and 7 is 11. Ooh. Now make that base 9. Wouldn't that be 1, 9, and 2 1s to make 11? So it does work. I really want you guys with me. Is everybody kind of with me? For the most part? Okay. So let me rewrite this. So here's one fact. This is one fact that we know. So then you can construct the other facts, right? So what's another fact that you know?
Seven plus 4.
Yeah, 7 base 9 plus 4 base 9, 12 base 9. Because no matter what the base, what property is that we used? Commutativity.
Oh.
Commutativity,
Yeah.
right?
Mhm.
Individuals commute, parentheses associate. Now give me some minus stuff.
12 base 9 minus 7 base 9, 12 base 9, 4 base 9.
Yeah, and then just the other way. So if I take the total minus either chunk, I get the other chunk. Right, so 12 base 9 minus 4 base 9 is 7 base 9. There's a 4-fact family, crazy. So there's a problem that references 4-fact families. Now you know what the hell they mean. And the problem kind of tells you, like they'll tell you this thing or they'll tell you this thing and you got to figure out the other 3. Maybe. Okay.
Yeah.
Alright, so that's one thing I left out of the 3-1 discussion. I think we did hit everything else. Okay. So, let's do this. Let's look at 3-2. We're gonna go over 3-2 and then I have a handout. See what you guys think about this handout. So let's go over 3-2. 3-2 is multiplication and division. Right, of course, division is where things get exceptionally freakier. Yes. Over there. So multiplication. Does anyone remember or know how we introduced the idea of multiplication to young people?
Time.
That's the name of it, but how do we connect it? So you're always trying to take a new idea and connect it to something they know. Yes?
Like adding the same number.
Yeah.
Over and over again.
So it's been a while for most of us since you've done 7 times 4 and you wrote 7 4s, right? But that's what we're talking about, right? So multiplication is fundamentally repeated addition. Which means, looking ahead, to do division problems, what could I use? Repeated, holy shit, right? If multiplication is repeated addition and division's on doing that, it seems like subtraction should come into play, and it totally does. So, one example, 4 times 7 is 4 groups of 7. So this would be 7 plus 7 plus 7 plus 7. And students at this point, when you go to start talking about multiplication, they've done all their addition stuff, they know addition pretty well, and that's why you want to try to build on that, right? And the memorization will kind of flow, but they'll see where this is coming from. They'll have a foundation to build that memorization on. What really sucks is when a teacher just says, memorize this, and they have no foundation of why it works to build on. That desperately sucks, right? And I see that not from youngins, but like older people, this teacher's just like, this is the way it's done, memorize it, and they have no idea why it makes sense. So this is amazing, right? 14 plus 14, okay, amazing. Amazing. Now, of course, I'm using this notation here. I kind of default to this. They're going to use what notation, probably? Yeah, so you can write this as 4x7, which we don't really like anymore because that makes it look like it's algebra. That looks like 28x. That's what it looks like to me, right?
Yeah.
Okay. What else? And of course, we could also use that. Right. I like it. So that's the kind of the basic idea of multiplication. So like we did before with addition and subtraction, we're going to talk about different models, different physical models you could use for this. Right? So this should be kind of immediately obvious possibly, but let's talk about the different models. Right? And then wait. So you could use, this should sound familiar, set model. So if I had to do something like 5 times 3, that means how many sets of how many in each set? What do you guys think? 5 sets with 3 in each set, yes? So the set model would be, what shape do you guys like today? Triangle, I like it. So. Oh man, you could have said so many horrible things. I was like, please do.
Octagon.
The Chinese symbol for 0. God. All right. And of course, what's beautiful about this is it reinforces the idea that multiplication is just repeated addition. You just keep adding 3 more until you get 5 total. And then you can just physically count them to get the answer, right? So you can have little shapes that they kind of put together. We're going to see that happen later with some of our little people. We'll see if we see any favorites come back. Put them down on the table, and then they can count them all up. And of course, you'll get, amazingly enough, you'll get 15. Spoiler alert. Okay. So that's the set model. What would be the difference? And this is where people kind of don't like Common Core, but physically, what would be the difference between this and this, of course?
It'd be 3 circles.
3 groups with 5 in each group. Now, it's kind of silly on one level, yes?
Yeah.
But they both correlate to different physical problems, don't they? If you have 5 rooms with 3 people in each room, well, this would be 3 rooms with 5 people in each room. That is a different physical setup. Okay, but I'm sort of on the fence a little bit, but I understand. There's a different physical setup, but it's the same answer in the commutativity and blah, blah, blah. I understand all that. Okay. All right, so you can do the blah, blah, blah. You can do the same thing. So another one, I don't know if you guys remember this from before. This is the measurement model. Does anyone remember what this one was basically dependent on? Measurement model? Number line. Right? So we're going to kind of expand that a little bit, the number line idea. This one is really simple. So if I had 5 times 3, so there's 1 3, 2 3s, 3 3s, 4 3s, 5 3s. Yay! Right? And again, to us, we see that as the same idea, but it has a very different feel to it, especially for somebody who's first learning this. This is based on motion, this is based on counting. Right, so if I move 3 spots 5 times, I've moved 15 spots. It's a different physical experience. I don't know how to say it. Okay. I don't think there was anything else there, no. I don't want to put it. I like it. So, and again, I could do 3 times 5, in which case you would do 3 steps of 5 each. Same idea. Now, then we have another approach called the rectangular array approach. Approach. There you go. So this is pretty much exactly what you think it might be. I don't know. I'm going to make a rectangle for one thing. You're like, okay, good. Now that word makes sense that it's in there. This is kind of, on one level, it's a little silly to me, but the set model, you would, if I'm doing 5 times 3, you would do 5 rows with 3 in each row, which is exactly analogous to 5 groups with 3 in each group, right? So instead of just sort of like throwing the groups all out there, you would line them up. This is exciting. Nobody will be seated during the trying to draw triangles scene. Okay, 1, 2, 3, 4, 5. We did it. But this kind of is a bridge. So this is 5, and this is 3. So this seems kind of silly to anybody else, do you? So all we're doing is we're taking this jumble, and we're organizing them. But now it's a little more direct. This is the number 5, and this is the number 3. So 5 times 3, it's a little more visually direct. This is the set model for rectangular array, and then you have the measurement model, which is kind of hilarious to me, but let me see if I can improve on the book here a little bit. Measurement model is a number line, yes? But of course, we all know that when we start talking about 2 different directions, don't I have a something times something else? I'm going to do like an XY thing. Oh shit. So I'm going to do, so in this case, I'm going to do 5, it's gonna look the same as this. Gonna do 5 of these and 3 of these. And I'm just gonna draw it out. To me, the really funny thing is, that's, instead of using triangles, I'm using squares, so they're basically the same thing. But again, this is using move over 3, then move up 5, and now fill it all in. So it's still, you know, a little bit connected to movement in this case. But I always think of it like an ice cube tray or something when I see that. And again, they can count these out. Ba 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 ba. Okay, so these are very well connected. They're almost the same thing, especially they seem to us like the same thing, because we know they all represent 15. Okay. How are we doing? All right. Nothing amazing here yet. All right. So let me erase this. Everybody ready? There's, I think this showed up earlier in the book, and I can't remember where, but there's something called a Cartesian Product.
All the different combinations.
Yeah. It's kind of nifty. So we have, let's say set A, so let's do an example. Set A is A, B, and set B is X, Z. So A cross B. So it's called Cartesian product, but I like the idea of cross product, because that kind of visually makes you think like this.
So
You're crossing things.
AX, BX.
Yeah, so it'd be AX, A, Z. Yeah, any way you want to do it. And then BX. You can do it, John. There you go, buddy. And B, Z. So it's just all the pairs that you can make.
But you wouldn't be able to do it XA, ZA. Like, if you were saying
It
that's
depends on, it kind of depends on what these truly represent.
Okay.
In general, yes, and you can imagine why. What do these look like?
Variable.
What do these little sets look like if I put numbers in them? 1, 3. Coordinates. So, in a sense, we do whatever's first should be the first elements, and whatever's second should be the second elements, because then it determines where they fall on the plane. But then again, who cares if our plane is this way or that way, right? I don't know if you guys are still with me. We just arbitrarily made this X and this Y. Why couldn't it have been the other way? It could have been the other way all day long. Totally. It could have, right? We could, instead of Y equals MX plus B, we could have X equals MY plus B. Totally could have. Just the other person woke up earlier that morning and said, let's do it that way. And the other guy got there, oh, shit, all right. All right, anything? Okay.
Yeah.
So that's what a Cartesian product is. Does anyone remember what this means?
Number of elements that
Yeah, so what's NA? What's that?
2.
2. Crazy. What's NB?
2.
2. And what is the number in A cross B? Holy shit. So, yeah. And real quick, it does not matter if there's an intersection between the two. In fact, they could be exactly the same. If I would have made this AB, this would have been AA, AB, BA, BB. They would still be 4 distinct points. You guys doing okay? So this is an example of an idea that you've used without realizing you've used it. And now we're showing it to you directly, finally, and giving it a name. Okay. Could you do, all right, could you do like A cross B cross C? Of course you could, because then that would be 3 dimensions,
Yeah.
right? Well, we're not, don't worry, we're gonna keep it flat, right? We're gonna keep it, okay. Blah, 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 yeah. So this would be obvious, yeah, 2 times 2 is 4. So this again is kind of like, it's not physical necessarily. These aren't objects, but it's still something you can visualize and see. All right. Then there's another idea. Has anybody ever taken any statistics or any probability or anything? A couple of you guys? Has anybody else taken a course? You talk about something called a tree diagram? Tree diagram? No? Okay. Don't worry, you don't have to be a great artist, right? I mean, here's my tree. All right, you got to think. There's Jeff's tree. That's about it. All right, looks like broccoli. Looks like something else. But a tree diagram kind of accomplishes the same thing we just did. It's just easier to keep track of things. Let me show you. So remember, a second ago we had A, what was it, AB, and B was XZ, right? So to do the Cartesian product, don't we choose one from here, put that first, and then don't we choose one from here second, right? So I choose A and I choose X, and there's a point. So here's what a tree diagram looks like. I got my first choice, and then I got my second choice. That is the word second, by the way. Look at that. Look at that. Could be the name Leonard. I don't know. I'm going to leave it. Okay. So your first choice, and this is a neat visual because you make decisions. You can think of it as going down a different path. You got the Rudyard Kipling well misunderstood poem about the path not taken, right? Anyway, everybody misunderstands that poem. But the first choice could either be an A, I can go down this path, or I could go down this path. Yes? That's my two choices. I could choose an A, or I could choose a B first, yes? No matter which one I chose, what could I do next?
Either an X or a Z.
Either an X or a Z. Either an X or a Z. And then to get the results, you just read them off. I go down the path. I could have gone down the A, X path. Or I could have gone down the A, Z path. And so forth. Right? And this is a beautiful visual of 2 choices times 2 choices is 4 total choices possible. I like it. This could start to explain to you, has anybody ever heard of the total number of pizza topping combinations that you could choose? Anybody ever knew that number? Anybody want to give an idea, give a guess as to how many total pizza topping combinations you could do? Let's say there's like, how many toppings do you normally choose from for those of you that eat pizza? How many, not that you personally take, but how many total choices are there at the place you go to? Anybody? Like 20? 20, 30, somewhere in this. All right, let's say 20. Give me a guess as to how many different combinations of toppings you could choose for one pizza.
400? There's 20?
I like it. The answer is in the millions.
Oh,
And
no.
here's the thing. So you could have a first choice, right? Now you could choose no topping, just cheese.
Yeah, okay.
Your first choice, how many branches are there? 20!
Oh, God.
Let's go on. And then off of there, now technically, all right, to make this simple, there would be 19. Is that cool? There would be 19 after that because you've already chosen one, yes?
Yeah.
And then there would be 18 after that, 17 after that. Do you understand what I'm saying? And depending on where you go, then most places don't really have a max. They're just like, if you want us to put it all in there, we'll pray that your dough gets can get through. Anyway, you guys semi with me? I mean, this is something that we can't intuit. We can't see that in our head ahead of time. We're like, there's 20 things. What do you mean there's millions of options? Because we can't stop to think about all the different ways to not only pair them up, but couldn't you put 8 toppings on? And couldn't each of those be any of the 20? Shua! It's insane. Okay. That's the tree from hell. All right, go away. You're scared. Stop. I've made pizza. No, I haven't. I can't make pizza batch. It's just good, no matter what I do. Blah, blah, blah. All right. So far, nothing groundbreaking. Few interesting things. We talked about millions of pizzas is always good. Now comes the part that we should really be really familiar with. We're talking about multiplication now, and we got properties. And they're basically the same properties as addition. So the very first one is closure. What did that mean again? Multiply whole numbers.
That if it's a whole number, it's gonna be.
Yeah, if I get two whole numbers,
The result's gonna be whole number.
and you multiply the results, a whole number also. I like it. Right? And I love that name, closure. I like it. So I don't know how to write it. You blah, blah, blah. So closure is also here. We got commutativity, of course, commutativity. Now, real quick, looking back at like our rectangular array method, what would commutativity mean? So we know that, let me make this easier myself. 2 times 3 is the same thing as 3 times 2, yes?
Yes.
All right, what would 2 times 3 look like in a rectangular array?
2 on one side. 3 on the
Yeah,
other.
2 rows, right? 2 rows and 3 columns, right? I'm sort of doing what do you call it, measuring line, who cares? 2 rows and 3 columns, and this would just do what to that?
Much still did.
Right? And of course, physically, it's the same thing. It can still hold as many ice cubes if you want to think of it as an ice cube tray. Right? So if I just turn it, that's a physical explanation about why the answer is the same, because it still holds the same amount of things. So that's a visual and a physical idea of commutativity property. Okay, I like it. And of course, what comes right after commutativity? Associativity. That's a little bit freakier. Now, associativity is nifty with multiplication. Associativity means parentheses move. So can somebody give me an example with some smaller numbers, maybe? Like, this is not enough, because to make it parentheses moving, there has to be at least how many things in a row here?
3.
There's got to be 3, so that I have a pair of them, and then I can move them. So I could do like this. Yes? So I can look at this. Now the book has got some pictures. I might want to, let me just tell you what page the pictures are on, because me trying to draw 3 dimensions. Yeah, page 104. They do a good job. But can you imagine what's going to happen here? I can't just have something that has a length and a width. I also need something that's got a height. So now these are rectangular solids. Are you guys with me? So like the base would be this, and then I would have 4 of them stacked up. Right? And depending on the manipulatives you have access to, you can actually get manipulatives to do that. Stack them up. Yeah, which is fun. And then you do math at the same time. Right? Subversive. So this would be a base of this, and 4 of them stacked up, yes? What would this be? A base of what? 3 by 4, right? 3 by 4, and then you'd have 2 of them. Yeah, 12, true, but like physically it'd be 3 by 4, and they have 2 of them stacked up, right? Maybe. And they do a good job. I mean, they kind of slice it differently. I'm not going to try to mimic the slices and all that shit in 3 dimensions, so you can look in the book for that. Okay, but it's kind of nice. You just have to step up 1 more dimension to show associativity. I like it. I think we talked about this already. The identity. What is it for multiplication?
You multiply by 0, it's going to give you 0.
That's not the identity, though. Identity is supposed to be the thing that I operate with that keeps it the same. 1, yeah. So identity is 1 because A times 1 equals 1 times A equals A. I love that idea. We sometimes math people pick the right word. Very often we don't. But identity makes sense. What do I use to keep something's identity the same? Not 2, because then it'll be twice as whatever it was. Right? 1, it keeps it the same. Now, catching up to what you just said, I think this is next. Sort of. Well, let's do this one next. There's another level of property that we can do now. These are all properties we've talked about before, but now that we have addition and subtraction under our belt, we can add on top of that some property that does multiplication with those, and that would be distribution. Right, so that would be now, okay, real quick. Let me give myself some room here. So we can kind of show, let me show you a couple examples. Let me do this first. Let me talk about this a little deeper. Deepier? Sure. Let's make up a new word. Deepier. Derpier? Yeah, I can do derp. What does order of operations want me to do first in this problem? What's in the parentheses? Can we do what's in the parentheses? What is x plus 2? Tell me. Tell me now. What is x plus 2? What is x plus 2? I love it. There you go. There's the right answer. All right? It's like you already said the answer, dude. Move on. So can I follow order of operations? No. But we know. Don't you know there's something I could do, yes? Do you understand why we're allowed to do it, considering what I just said? That goes against order of operations. So you're like, I don't know, man, what the hell are you talking about? Don't take that away from me. Okay, real quick. This is multiplication, yes?
Yeah.
What's the most fundamental idea behind multiplication?
Repeated
addition. So what does 3 times x really mean?
x plus x plus x.
I love it. Now use that here. What do I have 3 of?
X plus 2. X plus 2. X plus 1.
I love it. Go. Okay. Let me do this just to make it more formal. There we go. Yes, yes, yes. So I used something more fundamental than PEMDAS. Right? PEMDAS says the order operations existent. I used the freaking idea behind multiplication. So I'm not like finding a way around order operations. I'm rewriting the idea of multiplication. It is based on addition. And now what am I allowed to do?
Combine like terms.
How? Using what properties?
Addition. Oh wait, I mean, is it?
You can do it. I know this is really, really basic. Are the x's all sitting next to each other?
No.
So I can use commutativity. And of course I have parentheses, I have to use associativity. Right, but let's just cut to the chase. Right, we're like, yes, Joe. So I got 3 x's, and I got 3, 2, so I got 3x plus 6. And of course, whenever I show this in an algebra class, inevitably, before I can say anything, somebody says, wait, Waller, why are you making that so hard? You just do 3 times, and I'm like, ugh. I'm explaining why that works. It's a shortcut, right? That's what it is. So we would never do this shit in the middle. At least we wouldn't. But maybe your students would the first time you're introducing this, because you want to give them a foundation. Not just shit to memorize, but a foundation about why it makes sense. So this is what we don't do. This is the shortcut, but this is why the shortcut works. Okay, I like it. Has anybody ever seen that before? I'm sure you have. I probably just forgot about it. Okay. Now we can come back to what you said. Where am I at? This is the 5th one. So 6 multiplication by 0 is remarkably enough. What? What do you get when you multiply by 0? Holy shit. Okay. Right, because again, repeated addition. So if I write A zeros, I got nothing. Well, if I write 0 A's, There, I wrote them. I got nothing. Now here's where things get, let me see, is this too early? Yes, things get weird when we get to division. I'm getting a little too early. Of course, we all know things get weird when we get to division with 0, right? We'll get there eventually. Okay. Oh. Let me see. Yes. This should look familiar now. Let me see. I'm going to erase all this here. Okay. So, what your students are going to make, now this is definitely more familiar. We normally don't make addition tables that I know of, but I definitely remember multiplication tables. Right? Yes? So we got our, oh Jeff, you never can. Okay, so again, we have commutativity. So if you kind of draw a line roughly there, right? And again, the book's got this, page 106. Everything's on page 106. The easiest row and column here is, of course, what? 0, right? So that's the property, that's the multiplication by 0 property. So zeros and zeros, all right. And of course, the second easiest one, 1. And the second easiest because now I have to draw every single different symbol in 0. I just repeated the same symbol. But it's freaking easy as shit, right? 1. Good Jeff, good Jeff, good Jeff. 1. And then you got your 2, and then blah, 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 blah. Okay. And then you got the idea of doubling things, which we sort of had before with addition, right? We have that doubling idea that now we can kind of reinforce. So 6 plus 6 is 12. That means 2 times 6. 2 6s, 12, yeah. Okay. So the doubling stuff you got. What am I forgetting? Oh, so what's one of the easier count by? So when you're first learning numbers, and you want to count by 3s, count by 7s. 7s would be rough. Do you agree with me for a young one just trying to learn? What's one of the easier numbers to count by? 10 is definitely the easiest. Now take one step back from 10. 5. Right, because it alternates, ended 5, ended 0, ended 5, ended 0. So that's relatively easy. So you can do the 5s pretty easily because it's going to be, you got these already. And then 5, and then you got 10, 15, 20, 25, 30. So it's relatively easy to count by 5s. Yes, I like it. What else am I forgetting? Oh, all right. I can't remember. I forgot to look for this. I think this comes up. Oh, that's right. Well, it should come up now. Jeff, why didn't you find this? Let Jeff talk to himself for a second. This is really cool as shit, so if I can't find it, I'm going to show it to you anyway. I don't remember where this is exactly. I think it comes up later, but I might as well throw this at you now. Why not? Does anyone know something nifty about 9? That is such a wide open question. I love it.
It's like 1 less than, or like one of the table less than whatever.
Sure.
Like 3 times 10, 30, but then 9 times 3 is 3.
3 less, yeah.
3 minus 30.
What is 9 times 3?
27.
What's 2 plus 7?
9.
What's 9 times 8?
52.
What's 7 plus 2?
9.
What's 9 times 5?
45.
What's 4 plus 5? Holy, what? What? Anybody ever heard of it? Please don't. No, really?
Maybe, yeah.
So there are rules for every number 0 through 9. And 10, of course, is the easy one. There's a rule for 7 that I always forget because it's really kind of got multiple steps to it. And I just never took the time to memorize it. But 9, if I add up all the digits in a number, shit, now I gotta get serious. And they come out to be a multiple of 9. All right, so what's this? 5, 10, 13, 16, 18. Is 18 that's like my 15th puberty. Is 18 a multiple of 9?
Yes.
So 9 will go into this number, period. Try. Anybody got a calculator? Why don't you check your teacher? Make sure. If it doesn't go in, we can all go home. So you guys are like, oh, let me type this in wrong.
Yep.
Yeah, so if you do 9 into that, you get 1, 5, blah, blah, whatever, right?
Yep.
I like it. So that works. Does anyone know, so normally 9 is the one people know, and they don't realize there are ones for other ones. It should make sense that the rule for 3 should be about the same, and it is. 3 is exactly the same. So if you add up all the digits in a number and it comes out to be a multiple of 3, then 3 will go into it. So 3 and 9 are basically the same, which kind of makes sense because they're so intimately connected. Now, the proof of this is really nifty. I might leave that for later. I just want to say a couple more things. 2 is easy. Yes? How do you tell if something's divisible by 2? If it's even. 11. Yes? We already know 3. Now watch this. Let me ask you this. Okay, we can do this, Jeff. You can do it. Write it down. You doing it? Yeah. Does 3 go into this number? What's 4 plus 7 plus 4? 15. So 3 goes in, doesn't it? Is this number also even?
Yes.
So if 3 goes in and 2 goes in,
6.
6 goes in. That's the rule for 6. If it's even and the digits all add up to a multiple of 3, 6 goes in. So what's 474 divided by 6?
79.
I like it. Because I really want that to make sense. You knew 2 coming in, even. Now you know 3. So if both work, 6 works. Because 2 and 3 have nothing to do with each other, so they make 6 must work if they both go in. 5 is easy. What about 4 then? This is the last one I'll do for now. We'll do the other ones later. I'll look up 7 so I can show you. I always forget what that is. What about 4? How do you check to see if something's divisible by 4? This is different. What's 4 times 25? 100. So think about this. What we just said, 4 times 25 is 100. So does 4 go into 140?
Yes.
Because it goes into 140, right? Does it go into 1,040? Yes, it does. Because that's 10 hundredths, and 4 goes in each of those. So look, so I can keep going bigger. To check to see if 4 goes into something, it just has to go into the last 2 digits. So does 4 go into this number here? Yes, because it goes into 32. Funkadelic. Now I'm almost certain if you've never heard the thing for 9, you've definitely never heard of this other stuff I'm telling you. But let me know. Has anybody ever heard of this? Or
It sounds familiar now that you're saying.
Okay, good. Because sometimes it sort of like just escapes you. But I have this bad feeling that some people go through the school system and never hear this because it does seem like they're saying memorization is bad, which is dumb, because you got calculators now. Dumb, right? It'd be so cool to know this. This is just good to know. This is shit humans discovered, and then we're like, we're not going to tell other humans anymore. What? Hey, all right.
Like parallel parking.
Oh, God. I did my parking test with my mom's big ass station wagon. I'm like, if I can park this damn thing, I better get my license. All right. All right. And I'm thinking, and that was just last week. No, I'm joking. Let me see. Yeah, good. I like it. I like at the bottom of my notes, I have this thing saying turn over. Thank you, Fast Jeff. Let me think. Was there anything else I want to say about multiplication? I think that's, yeah, we sort of got into division there, so we might as well get into division properly. And the first thing I want to talk about, let's get this out of the way right now, real quick. Just on the side here. What is 0 divided by anything that's not 0? Yeah, 0 divided by any number that's not 0 is 0, right? And what's a physical representation of that idea. Like if I wanted to come up with a physical representation of this problem. So let's say there's 7 of us. 1, 2, 3, 4, 5, 6, 7. That's 7 of us right here, right? And we all go do a job. And then the person we did the job for says, I ain't giving you no money. So I got how much money to give to distribute? I got 0 money. So then how much do each of us get? 0. So there's a physical representation of 0 divided by 7. It's got a physical answer that makes sense. Are you guys with me? Some of you guys know where I'm going, of course, right? So what about a divided by 0?
0.
So let me ask you this. So this is a over 0. So what is 6 divided by 2?
3.
Why?
Because 2 goes into 6 3 times.
Good. Now tell me why this is true using multiplication.
3 times 2 is 6.
Yes. Any number that's the answer to division must multiply by the bottom to make the top, correct? So 6 divided by 2 is 3, because 3 is the number that's defined in such a way that when I multiply by 2, I get 6. God, that was a long-ass way to say 3 times 2 is 6.
Yeah.
Right? And I'm doing it for a reason. So what is 6 divided by 0? It would be the number that is defined in such a way that when I multiply it by 0, I get 6. Yes? That is what it means. What number is defined in such a way that when you multiply by 0, you get 6? Any number times 0 is?
0.
Do we have any numbers that are defined in a way that when I multiply by 0, I get 6? No. So that's why we call this undefined. Right? You guys have heard that term before, yes? So I've seen this before. This is OK, and this is a KO. Right? So when the 0's on top, it's OK. It's 0. When the 0's on the bottom, it'll knock you out. This is also known as the singularity, right? You guys okay? You guys okay? You guys all know the word undefined, but did you ever know why we call it undefined specifically? I mean, it's that simple. There ain't nothing defined to do what this says, so that's undefined. There you go. What about this shit? That looks like a giant division symbol, but that's 0 divided by the way, the division symbol itself, doesn't it look like a fraction with a placeholder for a number on top, number on the bottom? Anyway, 0 divided by 0. What is 0 divided by anything?
0.
What's anything divided by 0?
Undefined.
So 0 divided by 0 is both 0 and undefined.
It gives an error in the calculator.
Yeah, it does. This is, okay, I don't think the book tells you this, but this is something called indeterminate. It's worse than this. Did anyone call this a different name than undefined? When you divide by 0, you get
Impossible number?
infinite.
Infinite.
So sometimes teachers will call this infinite. When you're doing slope and you got rise and run and it doesn't run at all, it only rises, it means it goes to infinity in an instant. Yes? So this is like both 0 and infinity at the same time, which is why it gets a worse designation. We call it, yes?
What did that say again?
Indeterminate. In fact, I spelled it wrong because I just wanted to. There we go. Indeterminate. So I cannot determine what the answer is at all. This one, we know it's like infinity. Which is another way of saying it's not something, but at least we know it's infinity. This, it's everything between 0 and infinity. There you go. It's like, what? Okay. All right. Just wanted to talk about that real quick. It's 0. 0 finds a way to mess us up. Okay. So division, there's kind of 2 main physical problems that lead to dividing. There's an idea of sharing, and there's an idea, well, let's do this. There's sharing division, which kind of makes immediate sense. Sharing division. Sort of like that problem I just had a minute ago. So, what example did I come up with? Yeah, okay. So if I have a class of 20, it's the same problem in the book. Class of 20, and I want to divide into 4 teams. I could have made it $20 and I want to give it to 4 different people, but same kind of idea. I want to distribute, I want to share 20 amongst 4 groups, right? How many would be on each team? Holy shit. So it leads to division. Become a 20. Wow. Let me erase this in case anybody knows factorial. And gets on my case about that. The other one, measurement. Yes, you got it, Jeff. Measurement. Division. And let me use sort of almost the same idea. If I have a class of 20, and I want to put 4 people on each team. How many teams? And again, it leads to the exact same work, but even though it leads to the exact same work, isn't it a different physical conclusion? Right, up here I had 4 teams with 5 on each. Now I've got 5 teams with 4 on each, which is not, again, it's not like, oh my God, but there's still a physical difference between the 2 problems. Let me stop for a minute. So when you teach this stuff to students for the first time, a lot of what you're going to be using to teach it to them are things they could touch and move and put in places. These are 2 very different requirements for doing that. And I want to, we'll see this video in a minute. So like if I had 20 little triangles, it's too many to draw, and I want to put them into 4 teams, how would you do that? So you have 20 things on your desk. How would you start to put them into 4 teams? Forget that you know the answer, right? Yes? Oh, I see. Okay. So you would put 4 ones down, right? So for the 14, and then you just keep putting. I like it. That's exactly what you'll see. And then this one, class of 20, put 4 people on each team. What would you do physically then?
One. No, that's what
Just
you
group
do.
4.
I don't know how many teams now, do I? I know I've got 4 people, so what would you do?
I would group 4 to every.
Yes, then you would take 4, there's a team. I really want you to understand, I know on one level that's kind of silly and it's like, whoa, what the hell? But again, this is just next level shit to these people, yes? So they're gonna understand the difference, and it's a physical difference based on what they're doing with these little things, right? So it's like a different thing, but then when they get the same answer, you can say, this idea exists independent of the physical thing that brought you to it, right? 20 divided by 4 is 5, no matter what the shit you're doing physically, yes? But you gotta build it up to there. And that's a part of mathematics that people don't understand. You build it on manipulatives, you build it on a physical situation, but you have to move them in a position of you don't need the physical situation for the math itself to make sense and to work.
Right.
As some of you guys know all too well. The further you get in math, the less the physical situation kind of is there, but I won't. Okay. Blah, blah, blah. Oh, real quick. Before I forget, I've already forgotten, so let me go back. So just like before with sum and addend and all this kind of stuff. So when I'm dividing, this guy is the dividend, and this guy is the divisor. Now divisor should be more familiar, but dividend sounds like we're talking about business, and we're not. We're not talking about stocks. We're not talking about options or anything. We're Thank God, because I am the furthest away from a business teacher. Your business math is not math. All right, so this is kind of the physical idea that leads to the use of division, the different physical ideas that leads to it. So now let's talk about, we've got that, so now let's talk about how we teach students to do the actual work, right? And again, let's see if anybody was paying attention earlier. We're about to teach division to people that only recently learned how to draw two. Probably, no, maybe not, right? But relatively recent. So what do we want to build the idea of division on? Okay, we're going to get to repeated subtraction. We're going to get there. But what did we just do? If we're talking about division now, what did we just do?
Multiplication.
Multiplication, right? So do you guys remember with subtraction, there was a direct analogy to, not analogy, but a direct use of addition. When I did like 7 minus 4 equals what? It's the same thing as 7 is 4 plus what? What was this called?
Missing added.
Good. Because they can think 4 plus 1, 2, 3, 4, 5, 6, 7, 4 plus 3. Okay, so 7 minus 4 is 3. Because we built it off of something they feel relatively comfortable with. New idea based on something they feel more comfortable with, right? Which is something I try to do at every level of math I teach. Now, with division, if I said 8 divided by 4 is what, I can rewrite that, of course, as 4 times what equals 8. And at this point, they've done some work with the multiplication. They understand the properties. They kind of built a table. They might have memorized their table by now. Who knows, right?
Yeah.
So this question is a lot easier because they don't know what division really means. They haven't really put it in themselves. So they base it off of something they know, right? So remarkably enough, this is called the missing factor approach. Because the two elements of a product were each called factors. Okay. Bum, bum, bum. Oh, that's where I did it. Okay, I got you. So, I love this. All right. We're eventually going to get to repeated subtraction. We're almost there. We're almost there. I could do that next. Let me think. Yeah, let's do that next. I like that idea. Let's do repeated. I'm doing it live. I'm changing it. Is that meme still around? Yes? Okay, somebody at least says yes. Okay. Do it live. So watch this. If I wanted to do 44 divided by, let's start off with something that works, Jeff. 45 divided by 15.
You would subtract.
Yeah.
15.
So I could start, okay, 45 minus 15 is
30.
30. Minus 15 is 15. Minus 15 is 0. 1, 2, 3. I had to do it 3 times. That's the exact reverse of 3 times 15. Because this would be 15 plus 15 plus 15 to make 45, right? Again, when you introduce the idea of repeated subtraction, you build it off of repeated addition, right? And this is really reinforcing the idea that division is inherently the opposite of multiplication. Okay, this is exciting. Now, I like this. Okay, I like this change. So what if I wanted to do, what, Jeff? You could do it, buddy. Write down a number. There it is. There's a number. 50 divided by 13. Using the only method we know how, which is that one. What would happen? Do it. So 50 minus 13,
37,
37, minus 13,
24,
4, minus 13,
11.
11, and of course, can't do any more. So this will be 1, 2, 3, 3, what do you do with it? Remainder 11, right? And what that means, what that officially means, watch this. This is kind of funny. This is so simple, but a lot of times you're never told this and you never really realize this. I have 11 too much. If there was 11 less, what would this number be if there was 11 less? 39. 39 divided by 13 is 3. So this tells you how much excess this dumb thing had in order for this to go in evenly, right? And that's really kind of basic, but that's kind of like, a lot of times people are like, you don't think to look at it like that. Okay. Another thing is, what all this work tells me, look at all that work we did, oh my God. What all this work tells me is that 50 can be written as 3 times 13 plus 11. So this is just kind of another way to write a statement from a division result. Okay, so every whole number means the same letters they do. There it is. Given a whole number A and B, whole numbers A and B, and whole numbers Q and R, you can write A equals B times Q plus R. So a whole number is another whole number times this plus the remainder. And of course we use the letter Q here because this is the quotient. So like the 3 is the quotient, the 11 is the remainder. Right? And of course quotient is the main word we use for division. So like product. It's the main word we use for multiplication. Crazy shit. This is also sort of implying that A is greater than B. But it's all good. Oh yeah, I did that already. Okay, cool. I like that. So real quick, 68 divided by 8. Right? So this would be 68 minus 8, minus 8, minus 8. That's going to take a while, right?
Yeah.
Okay, so now, so the reason I want to say this is the impetus. Ooh, that's not a word I use much. This is the impetus, or the motivation, or the reason why we then move towards an algorithm. Instead of doing, obviously, what do we do? What would you have to do if you had to do this by hand? Would anybody do this? Unless only if I said, use repeated subtraction. Because you would lose all the points if you don't. What do we do, of course? Yeah, we do this weird shit. Unless you come from certain other countries, Russia's the main one that comes to mind, right? Of course, great thing to bring Russia up right now, but oh well. Just as one example where I know they do division completely differently. And then every time I have a Russian student in my class, I have to get them to show me because I always forget. Because this is, I've done this since I was tiny little, right? So of course this is really stuck in my brain. But we have to build our way up to why this algorithm works. You don't want to show somebody this first because they have no foundation on why this would work, right? Okay, so we're not there yet. Let me make sure I didn't miss anything. Good. So let me show you some, oh, I could show you this. Yeah, let's do one more thing and then I'll show you some videos and then we'll call it a day. We'll get out of here a little early. We deserve that, do we?
I had a question.
Yes.
When we divide 68 divided by 8 and we want repeated subtraction, would we be able to do 68 minus 16 since 16 is a multiple?
So I like that. That kind of is a step in the direction of why this works. So you could do, if you did 68 minus 16.
Yeah, just so it's like.
Yeah, then you're doing, so, yeah, if you did that, then, let's see if I can do this. Then each one of these would be 2 eighths.
Yeah.
So 2, 4, 6, 8, remainder 4, which is what we know it is. That is kind of like the next step to get them closer to the ultimate shortcut, right? Okay. And really, this is kind of like taking, instead of one step, you sort of jump and do 2 steps at a time. And of course, you could do 32, which would be 4 steps at a time. But then you just kind of lose resolution at the end if you take too big of a step. Okay. Oh, I was going to show you one thing. That's what it was. If I wanted to do, see what you guys think about this. If I want to do, do I want to do that? All right, let's do a smaller one. I wanted to do 25 divided by 9 using the measurement model. And then, how the shit will we do that shit? All right, so let's get 25 up here. Oh God, Jeff, let's see. Well, here's the idea. Sort of capturing the idea of subtraction, but visually it's interesting. Instead of subtracting from, we're building to. Let me start to do it and see if you understand. That's subtracting from. I'm going to build to. So if I take one step of 9, where am I? 9 is made. If I take another step of 9, I've not really measured this out too well. Oh, well, too bad. This will be 18. If I take another step of 9, it's too far, right?
Yeah.
All right, so there's 2 9s, and what's left here? 7. So this will be 2 remainder 7. Beautiful visual, yes? Reinforces counting by. Whatever the divisor is, reinforcing counting by that, right? And that's another big thing, is having them do certain methods. Not only will the method work, but it also reinforces earlier things. You don't want them to lose touch with earlier things that they've done. Okay.
For example, that method, what do you call it? Like the little house?
The little house. Oh, this.
Yeah, like that.
We actually, this is called, there's a really specific name for it, but it's basically the division algorithm. The standard division algorithm. Yeah.
So, say for example, they're like, oh, they go directly to 64. Would there be something, like other steps before they got to 64? You know, would they be like, oh, it's 64 and then, remainder 4? Like, they were, dividing that.
To do this, you mean?
Yeah.
Well, this one, what's really kind of interesting is, once they know their multiplication tables, there's a whole other way to look at division, which is 8 times what is close to 68. And
Exactly.
that's a different way to kind of think about it. This is sort of like, as they're still grappling with that, this is giving, subtraction is something they're really comfortable with. But they're still getting used to the other things, so then you can bring in that way of looking at it, right?
Okay.
And what's really nifty is, for us, what do we wish was up here? 64, right?
Yeah. Right.
64 divided by 8 is 8. 4 divided by 8 is a half. Oh shit! Oh shit! Sorry.
Okay.
Some fractions
Yeah.
coming in. Somebody always freaks out when I bring fractions in. And this is really 8 remainder 4, because what's half of 8? Frickin' 4. So there you go. 8 and a half of 8 is what it means. So 8 remainder 4. Crazy. Sound like McConaughey. All right. Okay. Was that the last thing? Yeah, that was the last thing. Let me show you some cute kids doing some math. There we go. Oh yeah, I can't record this, or the author will